Okay, now in the last part of the lecture, we talked about the ability to change our state variables. And if we were to change our state variables, then we could change the ABCD matrices or vectors that are used in the state equations. And I keep saying that we're going to want to change our state variables in order to do things from the point of view of modern control design in terms of gaining some insight into the system and getting assistance in designing a controller and things like this. And so now I want to sort of go down that path. So far we just know that it's possible to change our state variables, and there are many choices of state variables. But exactly which choice should be the one you use has been something I haven't answered. And so I'm going to give one particular example right now, which is imagine a set of state variables that would allow us to diagonalize the A matrix. And what I mean by that is when we take the original set of state variables and whatever A matrix you wind up with, can we convert the state variables to a new set so that when we apply the similarity transform to the A matrix, we wind up with a diagonal version of A. And if we do that, then that's going to give us great insight into the dynamics and some assistance when it comes to the control of a system from the point of view of using state space equations. So to begin with, we just want to talk about how would I go about finding this special set of state variables, and in fact what is the similarity transform, meaning what is the linear combination in the form of that P matrix and the P inverse matrix that would make this all happen. So we're going to have our set of state equations. A x the vector plus bu equals x the vector dot, and y equals cx the vector plus du. And we've chosen some arbitrary set of state variables. Probably what we would do is we would have a physical set like position and velocity. That's probably how we got to this set of state equations to begin with. And now I want to do a change in variables. I want to choose a different x1, x2, dot, 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 or x vector in general, so that I rewrite the equations and the A prime matrix, or the new A matrix, is now diagonalized. In general, when we started, it will not be a diagonal matrix. Well, it turns out that I can go through a process and I can take the A matrix and I can find the eigenvalues and their associated eigenvectors. So I can find eigenvalue 1 and its associated eigenvector 1, eigenvector 2 associated with eigenvalue 2, and so on. And when I do that, if I create the linear transform matrix P such that it is all of the eigenvectors as row vectors, then when I apply the similarity transform and I wind up with a P inverse AP, this will be a diagonal matrix. And the diagonal matrix will have the eigenvalues on its diagonal. The order of the eigenvalues will match the order of the eigenvectors that I put in the P matrix. Okay, so this means that I can figure out what the magical set of state variables are that diagonalize the matrix by coming up with the linear transform matrix P that is based on the eigenvectors of the original A matrix. Okay, so I'm going to say that again. I'm going to take my original A matrix. And the original ABCD was premised on the inputs and the outputs and some choice of state variables. And what I want to do is I want to have a diagonal form of A. And I'll explain why in the next segment. But the diagonal form of A is going to be a very powerful representation of the state space equations. And so the question is, what set of state variables do I need to choose in order to convert the state equations so that A winds up being diagonal, or the new version, the equivalent version of A, is diagonal? And it turns out the answer is captured by the eigenvalues and eigenvectors. The diagonal matrix itself will be the eigenvalues on the diagonal. And the way I get there is I find the associated eigenvectors to create the linear transformation matrix. In fact, I know right off the bat what A will be, but I'm going to need P and P inverse to figure out what B, C, and D are going to be so I can write the complete set of equations properly. Okay? Now that's a lot of information packed in a couple lines here, so we'll do an example, and we'll take an A matrix that we've been using before. So let's imagine A equals 4, 2, 3, 5. And we can go through a process to get the eigenvalues and the eigenvectors of the A matrix. It turns out we've done an example with this already. So I'm just going to write down those values. Turns out that eigenvalue 1 is 2, and the associated eigenvector is 3 minus 2. And second eigenvalue was 7, and the associated eigenvector was 1 and 1. Now these are the eigenvectors that haven't been normalized, but any constant times the eigenvectors is also an eigenvector. And so what I'm going to do is I'm going to make my transform equation P equal to the columns, or I have its columns be the eigenvectors. So I'm going to have the first column be V1 and the second column be V2, which means the P matrix is 3 minus 2, which is my V1, and the second column is 1, 1. When I do this, I can also figure out what P inverse is, and I'll let you figure that out. But the answer is going to be 1/5, so 5 is going to be the determinant. 3 minus a minus 2 gives me a 5. And I'm going to flip the values and negate those, and so I'm going to get a 1, 3 minus 1, 2. So there's my P inverse matrix. And now, when I want to find my new A matrix, the A prime, that's P inverse A P. And when I take that and multiply it out, I'm going to wind up with a 2, 0, 0, 7. And I'll let you go ahead and verify that. But if I multiply this out, P inverse times the original A times P, P inverse AP, I'll wind up with 2, 0, 0, 7. And lo and behold, the eigenvalues are on the diagonal. And in the order, eigenvalue 1, eigenvalue 2, because my P transform had eigenvector 1 first and eigenvector 2 second. If I'd flipped those, then I would have had a 7 and a 2 there. Okay? So there's my A prime. And as it turns out, if I were to have had a full-blown set of equations, I now have the P and the P inverse, and I could go ahead and transform B and C as well. If you remember, the B prime was a P inverse B, and the C prime was a C and an M. So just for the heck of it, had we assumed that, let's say that B was a 1, 2, and that C was a 1, 1 in the original set, when I multiply all this out, for this particular example, I'm going to wind up with a minus 1/5 and an 8/5 for the new B. I'm going to wind up with a 1, 2 for the new C. So, if you allow the linear transform matrix to be the matrix of eigenvalues of the original A matrix, you're going to get the equivalent, the matrix that allows you to convert your set of state equations to a new set of state equations that have been diagonalized. And by diagonalized, I mean the new effective A matrix is now a diagonal matrix. And the values on the diagonal are the eigenvalues of the original matrix. Now what we actually haven't done is figured out what those new state variables were. Well, that's easy because the state variables were Z, the new state vector, was P inverse times the old state vector. And so if I want to figure that out, I'm going to take the P inverse The P inverse in this case was a 1/5, 1 minus 1, 2, 3, and I multiply it by my x1 and my x2, whatever they were. So if this was, say, position and velocity, that could have been it. It could have been something else, whatever you wound up with to begin with. And when I go through and do this and multiply it out, it turns out that I get a new first state variable that's 1/5 x1 minus 1/5 x2. And the second state variable is 2/5 x1 plus 3/5 x2. Okay? So the trick here is, if you were to choose a new set of state variables with this relationship, take your original x1 and x2 and subtract them and multiply by 1/5 and make that your new first state variable, and then take 2/5 of the first one plus 3/5 of the second one and make that your second state variable. But that's the magic point of view. That's the magic state variable perspective that winds up diagonalizing your original A matrix. Okay? And the process comes down to this. Write your equations given your original choice of state variables. Take the A matrix, find the eigenvalues and eigenvectors, and then make your linear transform matrix P be the matrix of eigenvectors. When you do that, you'll wind up diagonalizing your entire system. And in the next section of video, we'll talk about how that is a very fantastic point of view for your state space representation of the dynamics of your system.